Good morning, Professor.
Good morning.
So, November 1st, there's an RC event where I'm going to be meeting Space Workshop on Friday. Would that be an excuse after this one?
So follow the protocol, do self-reporting, and yeah, that should probably be it. I mean, is it through? Yeah, I mean, it would be good if there was something that right? Yeah, they usually they can send me a message, and they should probably. I think it'd be advantageous to you for that message to be sent to all your classes.
Thank you.
This was a conventional show. This was a here. Asked for the special that part.
So instead of, but I think what's that?
That was.
It was like reference was in
Yeah, sorry. So the election potential.
and I was like, so just before, right? And he's like,
Okay. Welcome everybody. How's it going? How are things going? Good? No exams this week, really? Or yeah, you're in kind of cruise mode, right? For a little bit, hopefully, or some other classes. Yeah? No? Yes?
We had a physics exam.
Okay, you had a physics one? Okay, all right. Is that like a one midterm, one final type of class, or are there multiple?
There's one more midterm, but for this week at least.
Okay, all right, great, thanks. Okay, so yeah, the exams are graded, and Proj is working to get those scores posted. Okay, and then I'll send out a message about the distribution and some other things. But if you have questions about the grading of that exam, what will happen is we'll put, I think there already is an exam one assignment, and so you can take your exam and take another sheet of paper, write any issues you might have with the grading on the exam, and explanations on the front on a cover sheet, okay? Scan the rest of, scan the entire exam, of course, and then with that cover sheet and the scanned exam, we'll go ahead and we'll do reviews. That needs to happen before the next exam. The next exam is currently scheduled for November 19th, and we're going to stick to that. Okay. Any questions administratively about how things are going in the course? Okay. I'm a little behind on things. I've got some stuff going on. So thank you for your patience. I think we've got most things taken care of. Proj is working on the attendance, so if there's still issues there, send a message to Proj, okay, and me, okay, so that we can get that resolved. Any questions? So that's administrative stuff. The labs seem to be going pretty smoothly, so thank you for your cooperation there. There does seem to be an issue with the pre-lab survey that's being issued by another professor. If you have an issue and we can't resolve it, then just take a screenshot of the error message you're getting and put that into Canvas, all right? Of course, we want to facilitate the data that are being collected, or we want to facilitate the collection of the data, but we're going to be understanding in terms of grading perspective, okay? Well, let's go ahead and get going. This is our third session on beams. And then on Friday, we'll have our fourth session on beams. And then we'll step away from these beams for just a little bit, but we'll come back to them near the end of the semester, okay? So what should we be able to learn today? Well, we want to be able to relate the radius of curvature of a beam to local strain. Okay, you're like, what does that mean? Okay, well, we're going to talk about how these beams curve again, all right, and this time we're going to discuss how that affects the strain along that beam. Okay, and the other, and there'll be tensile and compressive strains, and it will look something like this. So here's a beam that is being bent, and there is some radius to that bending, okay? And we'll discuss what the local strains look like along that beam. And then the other thing that we'll look at is in relating the internal moment to the normal or bending stresses within a beam. This is kind of a big deal, and it gets a name. It's called the Flexure Formula. Very creative, I guess. But that formula is going to be something that you can take with you, and it may even come up in an interview. It did for me for a job interview once. They wanted me to be able to calculate the bending stress along the beam. So after today, you'll have that key tool, and that will be something that I don't expect. None of us is going to really remember all the equations that we discussed in this class, but there are a few key ones that we do remember. Flee would probably be one. The difference between stress and strain. I had another friend who told me he was walking out of it, or he was walking into his interview, and his buddy walked out of the interview, and the buddy was like, I couldn't remember the difference between stress and strain. It was like, right? So hopefully those types of concepts will stick with you. And of course, we have some ideas concerning the bars and the rods and the beams, and a little bit on the trusses, right? But that's really what we're covering. And maybe I'm a broken record here, but I'll say it again. If we understand how the loading that we apply to these simple structures affects the stresses and the strains in them, it will be essentially pretty straightforward to figure out what the stresses and strains mean in much more complicated structures, right? So these kind of test structures are the base cases that build your toolbox so that you can conceptualize, what is a shear stress? What is a normal stress? What is a shear strain? What is a normal strain? And is my material going to fail or not? Okay? And we're going to spend a decent amount of time looking at different aspects of how do you figure out if the stresses exceed the effective yield strength? Or how do you figure out, maybe better said, how do you figure out how the effective stress that you have in your system compares to the yield strength of the material, and whether or not it's going to fail, right? Because at this point, you should already be thinking, wait a second, I have a pretty good idea of how the yield strength compares to a normal stress. But what if I have normal stresses and shear stresses? Or what if I have normal stresses in multiple dimensions or multiple directions, and how does that compare to my yield strength for the material? That's another one of the essences or the essential pieces of information that we get to in this course. All right. Yes, and we'll talk about tensile and compressive stresses. Any questions, any insights up to this point? How are you feeling about beams? Did you enjoy the graphing techniques now that you have in your toolbox to figure out what the internal shear forces and the internal bending moments are? Okay. Do you enjoy these integral differential relationships? Do you enjoy figuring out what the boundary conditions are on the left and right? Maybe not enjoy, but you have it under your belt, right? Because the other key thing, and maybe this is foreshadowing purposely, so right, we're relating the internal moment to the normal bending stresses within the beam. The reason why we care so much about, calculating out shear force is so that we can figure out what the bending moment is, okay? And once we know the bending moment, then we have the opportunity to apply what we're going to call the Flexure Formula, right? It's here. The internal moment is very much directly related to the normal stresses that you have in the beam. Okay? So in order to be able to calculate those, just like it's like this same old pattern. You spent a lot of time in statics trying to figure out what the internal force, internal bending moment, or internal shear force was. Okay? Then we said, hey, there's a way to figure out what the stress is for bars, and the stress is, or are, the stresses are for rods. Okay? And so we're going to do the same today. We're going to do that except for beams. Now, here's a kind of a review. And what are we talking about here? We're talking about one of the very simple base cases for a beam and a transverse load on a beam. All right, so this is a cantilevered beam, and it has load P on the end, and we've already done this problem. All right, in fact, twice you saw that I made mistakes in the slides on this exact problem. Okay, and you apply external. I'll go through this quickly. Don't worry too much. All right, but we would go through external equilibrium, okay? And we're going to know that we have a reaction force and a reaction moment on the left side, right? A wall gives us those two constraints. We are going to sum the forces in, let's say, the vertical direction, and we get that R and P are equal to each other. And we're going to go ahead and sum the moments about a particular spot. In this case, we selected O, and they have to be equal to 0. And so then we have our MR and our PL. That is just for the external equilibrium, right? But then, and so, MR is going to be equal to PL, okay, like that. And then, right, what's next? Well, we have different options, right? We could say, I'm going to do straight up equilibrium like I did last semester. Or I am going to use the integral differential relationships, all right? In either case, it's not a bad idea now that we've talked about this quite a bit, to go ahead and look at what the values are just to the left and just to the right, or just to the right of the left side and just to the left of the right side, okay, to be able to figure out what the boundary conditions are. So, if we're looking at the left end, okay, we would have our shear force and our bending moment as described here. And these are, sorry, I guess I was pointing to things, but but you didn't see that. They're described here, right, with this convention. If I cover up the right side, V is down, and the moment is counterclockwise, okay? And we're going to say, we're going to just go a little bit, all right, a little bit to the to the right of the left side, okay, so for small x1. And we're going to have the opportunity, right, to come up with the internal shear force and the internal bending moment right there at the left side. And for the right side, okay, we're going to do a similar drawing. And at this point, I think we went through things a little bit fast at some points in the last meeting that we had, but there should be an appreciation now for how going from a different direction affects how we plot things. Okay, what do I mean? I mean, in particular, maybe the simplest examples are when you have that concentrated moment, where you have that a concentrated force, right? If I'm going from left to right, then if I have a force being put upward, like located along the beam, that's going to be a delta V going from left to right, positive F, whatever that applied force would be, upward. Right? But if I'm coming from the right side and I hit that force going upward, that's actually a jump down, okay? And the same thing is true when you have these MAPs, these concentrated or these coupled moments as we call them, okay? So here we follow the convention, and again, I'm probably saying it ad nauseum, the external, like this, when I chose this R and I chose this MR here, I didn't really, I was just using whatever my gut told me would be a great idea, okay? And, but ignore that gut feeling, all right, when you start looking at the internal bending moment and internal shear force, okay? You gotta follow the convention. Okay, and then again, we go for small x2, and we can look at what's happening at the right side. So you see, this is another thing that we'll talk about in more depth later in the class, but you see this shear force, x1 equals L, right? So x1 equals L, that would be, this is x1 over here, that would be all the way over to the right side, okay? Or you can say that x2 equals 0, all right? That's also all the way to the right side, okay? And they're going to be the same. And I think, I can't remember who it was, but thank you for that nice question that we had in the last class about, hey, why, how is this V, right, that's upward, and this V downward, how are they the same, right? And we kind of went through that. And we also went through the analogy of the axial loading, right? That if just depending on which side you cover up, when you do an internal slice on axial loading on a bar, okay, you're going to be getting a vector that's going to be in the opposite direction. Okay? So we can figure out what the boundary conditions do to the internal shear force and the internal bending moment, okay, at the right side, just like we did at the left side. And if we use the integral differential relationships, right, here we see that we have V is equal to integral of W dx, right? That's just one of our new forms of equilibrium, okay? And this comes from, of course, dV dx is equal to W. We use that. You can always use this, okay? You can always use this relationship even when there is no distributed force, right? We see there's no distributed force across the top of that thing. So W is equal to 0. Plug that in. We get a, since this is kind of indefinite integral, the way it's drawn out, we can say that's equal to C1, and we can then apply this boundary condition V of 0 is equal to P, all right? Or we could have applied this boundary condition. Notice, what's nice, when you don't have any external load acting in the middle of your beam, okay, along your beam, you only have to essentially perform one set of integrals. Okay? When you have like if you have an internal force, or not internal force, you have an external force or a couple of moment being applied, okay, then essentially, you know, we have defined our x1 and our x2 here, but that's when you're going to want to think about, okay, I'm only going to really think about my integral being effective until I get to that external load, okay? Or maybe my distributed force shuts off or turns on, okay, somewhere across that beam, right? But that's that your integral is going to go up to the region where something externally is changing. We can figure out, okay, then that this V, the internal V, is going to be equal to P. That's pretty straightforward. So when we draw the shear force diagram here, we're going to get that we have just P across the entire length. With the differential integral relationship for moment, we have that dm dx is equal to V, okay, and we can then integrate the V to get the moment. Okay, integrate the V with respect to x, like we see here. And we can say, all right, I have my C1, right? That's going to be C1x and then plus some C2. And once again, we're going to make use of our boundary conditions, right? And we have two. We have one where m of 0 is equal to minus PL. And we have another where m of x1 is at L is equal to 0. Okay? So it's probably easier to plug in x equals 0, so that C2 is just equal to minus PL. Okay? So that is the boundary condition, and C2 is going to be equal to minus PL. And that means that the expression that we have, okay, is going to lead to a graph where we start down at minus PL, okay, and we come back up like this, with the slope, of course, being equal to P. Any questions on this? All right. So, you know, you can very much imagine on exam 2, right? You're given some type of beam with some loading. Obviously not this simple, okay? Unless, like, you know, it's a question of where is the bending moment the largest, okay? And that will be something that you think about in terms of the magnitude. Why would I want to know where the bending moment is the largest? Well, I want to know where the bending moment is the largest because that's going to be dictating where my stress is going to be the largest. Again, foreshadowing. You're going to see that in a few minutes. Okay? That since we want to know where stresses, normal stresses, are going to be largest along a beam, okay, and they're coupled to the bending moment, we care very much about the bending moment, right? So a very straightforward problem would be, here is a beam. give me the shear force and bending moment diagrams. Now tell me what the distribution of stresses would be across that beam or along that beam. Okay? And that, I mean, I would just plan on that being one of the questions. Yes?
Why for the moment equation for the integral is it dx?
Why? Okay, that's because, let me just write here. Okay. Remember that we have that dm dx is equal to v, right? So then I multiply both sides by dx, right? And then I take the integral. Okay? All right, no problem. Okay, so now once we have this ability to write out the, these shear force and bending moment diagrams, we're doing awesomeness. Okay, that's great. What does it really look like, though? Okay, and these are going to be my very crude drawings. Okay, so that is a beam. I've drawn these boxes so many times. My daughter came to the office one day. It was multiple kids came to the office, and I was like drawing. I was like, okay. So they're like, so what do you do? And I was trying to draw something, just on the chalkboard for them, and I just did like this very simple perspective. It's like, wow, you're good at drawing. I'm like, no, not really. I just know how to draw boxes. Okay. So here's a box. All right. Let me see if I lost my thing. Hold on a second. All right, so here's our box, and here is the beam that's kind of connected to that box. It has some length, and it has some force P, like we see there. Okay, and if we, this is the entire beam. If we slice this system, as you see here, okay, and that's my way of saying that's sliced. Okay, imagine you have a really bad knife, and it's like, making the edges all look serrated like the knife itself. I am going to be able to draw a shear force that is following my convention. So what is my convention? If I look at this thing, right, I've kind of cut the right side, or I've removed the right side. I'm covering up the right side, right? And so remember this convention, this is the V that I have, right? So that's going downward. So if I slice it and I'm looking at it here, I'm going to say that my V is downward and my V is equal to P. So that should give us a little bit of an idea of what's happening. Now, we won't talk about these shear forces today. Okay. We are talking about the shear forces. We won't talk about the shear stresses that are related to the shear force today, right? But can you imagine? This is a force acting on a surface parallel to the surface, right? So what does that mean? That means that there are going to be shear stresses that have little itty bitty forces, right, associated with them on the little DAs. Okay? But we're not going to talk about that today. Why do we wait to talk about that? Because for long beams, and I'm talking not even that modestly long beams, I'm talking about something that you wouldn't put in a scissors. Okay? Right? Scissors, I'm getting off on a tangent, right? Anyone used scissors before? No, you've never used scissors. Okay, well, that's great. It's just an abstract idea of what scissors are, okay? Why do we use scissors? Right? Why don't I just take my piece of paper and try to pull it apart? All right, why don't I just, and sometimes you do, right? Like you fold it, you lick it, and then you tear, right? But that's an interesting mechanism too, tearing, right? But why do we use scissors? Well, it turns out a couple of things are involved. One, scissors are very good at applying a shear stress, right? You've heard of shears, right? They call them shears, and lamb, they shear the whatever, right? Those are shears. What is what's that guy's, there are all those British cartoons with the sheep. Shaun the Sheep, right? Shaun the Sheep, but what's the guy's, his owner's name is? Wallace and Gromit. Okay, anyway. Yeah. Shaun the Sheep is one of the sheeps. One of the sheep, right? Plural of sheep. Anyway. All right, so shears, right? Now you have an indelible image of a shear, okay? They apply two forces with a very small distance in between them. Boomba! What's that? What's up, right? You got now force parallel to area, right? Now you're like, oh, that's a shear stress. Big time shear stress, right? Shear force over area. And it turns out, as you'll see, that the ductile materials, in a little bit, like a few classes, the ductile materials, they are much more sensitive by a factor of 2, essentially, to shear stress. Shear stress dominates their failure. So if you can apply a lot of shear, okay, then you have the opportunity to essentially cut materials. And anyone use the shear in the machine shop? Anyone scared of the shear in the machine shop? Ka-ching, ka-chunk, right? Like, it takes those pieces of metal, very thin pieces of metal, or pretty thin pieces of metal, right? And it brings two blades very close to each other, and it shears them. Okay? So anyway, beams do not, that's what I'm saying. Like, essentially, as soon as I get my two scissor blades far from each other, right, shear is not going to be very high. And so we don't talk about shear very much until we do, okay? And it's actually kind of a painful calculation. But it turns out that bending moment, where is it? Okay, this, all right, bending moment, px, all right, or minus px, or however you want to look at it, okay? That is what's going to be dominating the system. So this is really, I guess what we should say really is that this is this is L minus X, right? This really is, at least with X being defined, from this side. Okay. You get that? And this is actually drawn the wrong direction on top of that. So I'm going to draw it the other direction. Okay. All these interesting things that you see when you review your own work. Okay. Any questions on this? Okay. Good. So the bending moment is something that you can see, but it's still maybe a little bit harder to get a feel for what it really means, right? This is a little bit, how do you say, it's a little bit abstract, but I think once we talk about the deformation, so the strain associated with it now, you'll get a better sense of what is happening. But one way before we even do that is, if I were to like grab somewhere along this axis, right, and I was just able to like put a screwdriver there and I was able to twist, and okay, or twist the other direction, right? That would be essentially the moment that it's feeling. Okay. All right. Let us continue. So if now you already have an idea of how to apply a torque to a shaft, right? And that's like, essentially you can think of it as the screwdriver, right? The length of that shaft that's going in to the screw that is trying to either tighten or loosen, okay? And so now what we're going to do is we're going to apply, something that has units of force times length, and we're going to apply that to a beam. Okay? So here's another one of our beams. And we're going to say that it has some coordinate system like this. And we're going to apply some type of moment to it. All right. Now, if I take this lovely chalk eraser, this is going to make my hands all messy. All right. So if I take this, and this is hilarious too. This is not. This is great. This is not really for chalk, right? This is actually a dry erase. Yeah, it even says it. Okay. But anyway, if I take this, and now you see I've got a moment that I'm applying. Oh, right, and I'm applying. That's actually pretty. This is the power of surfboards right here. Anyone surf? Right? We had a surfer, right? Yeah. You surf, right? So why is this demonstrating the power of surfboards? That's right. It's got an off, so it has a foam core, right? And that foam core is pretty thick, actually, right? And it has a very, very thin shell around it, which is usually, well, if you use the kind of boards that I use, they're cheap. So, you know, some type of fiberglass, right? But high-end stuff now that people use carbon fiber composite and all that jazz, right? Or straight up epoxy with a, yeah, it just depends. But anyway, so, you know, you see, that's actually pretty, I don't want to break it. I think I could break it, but I'm not going to, okay? But you see how this is bending a little bit? And and you see my hand is, it's applying the bending moment, it's applying a moment just like that. And I'm not really applying a force. If I was doing like this or this, that would be a force. But really, I'm applying a bending moment, okay? That's pure bending moment here, okay? I mean, it's not pure, but it's pretty pure. Yes?
Doesn't applying a force also then apply the moment also? Because
Okay. So when I applied a force at the end, was the bending moment across the beam, along the beam constant?
Quickly, no. If the other side is anchored, then
No, right, and no, right? But if I take this, okay, and all I do is I apply a bending moment, and even if this is a wall, right, and theoretically, since it's some type of cool bending moment, without applying any force, all right, then the moment across the beam is going to be constant. Okay? All right, that's what we're getting at. Yes?
So if the foam withstands the bending, so does the string tension?
Well, it helps even better, right? So you have foam, so you use thick foam to help with the bending moment, right? But the stringer, right, is this piece of wood that has much higher strength than the foam, right? And so a surfboard is a composite in multiple ways. It's a composite in terms of its structure, all right? But when we usually refer to composites, what we're usually referring to is fiberglass plus some type of thermosetting material, like a urethane or an epoxy. Okay? So you're absolutely right. We still need the stringer. It's not. But what's surprising is you take something that's so wimpy-woppy, okay, like foam, and you just make it very thick, and it has a surprising amount of resistance to bending. Okay? That's what we're trying to get at. Good point, though. Okay? So, do you surf as well? You must, if you know what a stringer is. Okay. Yeah, stringers, for anyone that's interested, are pieces of often balsa wood that are thick that go along, and they actually glue foam to either side of these stringers, or some boards have, like some of the soft tops, they have like multiple stringers through them. Okay, or people have even tried to make travel boards where they put like a fiberglass rod in it, and then like you can like disassemble the board and like then pack it in like a suitcase form. And when you're ready to use it, you like stick these rods in it to connect these fiberglass pieces. Or boogie boards now have actually fiberglass stringers as well, the high-end boogie boards. So they're very important. Okay, so what's going to happen? Well, it's going to look something like this. All right. And this may be the best drawing you get from me all semester, and I'm not even doing it real time, right? I'm sorry, I'm not very, they say there's something like, sympathetic chalkboard writing. I'll try to go slow, but I'm not super sympathetic, am I? All right, but you do have the slides. So what do you notice about this? There are a couple things you can see. What do you notice? Just no math. Yes, Mark.
Top is wider.
The top is wider. Okay? Why is the top wider? I mean, does that make sense that if I were taking this thing, that somehow if I were taking this this piece of beam and I'm applying a moment to it, why would the top get wider? Yes.
It's the top's pressure.
Yeah, that's exactly right. You can see that. You can feel it. Take your pencil or whatever it is, right? This is a key principle today. Or eraser, better eraser, right? If you apply this type of moment, or you take that cool, is that electric? Is that electric over there? All right, yeah. Those are fun. I've only been on one for a couple seconds, but they're fun. Okay, so yeah, whatever. I got. That's an awesome thing. All right, I'm distracted. Okay, so you see that as I'm applying this bending moment, the top is going to be in compression. All right, and you know one way to look at it is you see this point right here and this point on the top. Both of these points on the top, as I apply this moment, they're getting closer to each other. Right? They're getting closer to each other, and the points right here and here on the bottom, they're getting farther apart. And that is quintessential compressive strain and tensile strain. Yes?
So how does this compression relate to the buckling of the material once you push even harder?
Okay, so, yeah, okay, so buckling so buckling by definition is not related to the strength of a material. It's related to kind of the stiffness of the material, the elastic modulus of the material. All right, and we're not going to cover buckling in this semester. We'll cover it in the next class. Okay, but yeah, what happens is if you make your beam super long, okay, there becomes what we call a slenderness. Right? Like if you just take a constant cross section, like if you take me and you just extend me by 2 feet, so that like I would be a reasonably sized basketball player. Okay. Well, actually, I'd be a foot. If you foot and a half, right? You get a basketball player, and if you keep my, I'm not like anyway. I'm what I am. I'm okay with my body image. All right. So, but if you did that, right, I would be slender. Okay. But I'd also be more susceptible to buckling out, okay? And so what happens is as you make something more slender, that's going to cause buckling. But the bending moment could be the same across that entire length, right? What we're talking about is, and it is related to the bending moment, in fact. What happens though is that the slenderness plays a role. And the Romans figured this kind of thing out too with the columns that they built. Okay. All right, so why does it get fatter then? So we said it was in compression, but why does it get fatter? Yes? Poisson's ratio, right? So now we know that right, because that's in a lateral direction, right? Orthogonal to the direction in which we have the axial stresses, right? And so, or the axial strains, better said, right? So that now we know that it's getting fatter because it's getting wider at the top because it's experiencing compressive strain. And the Poisson's ratio says, well, if it's compressive, it's going to get wider. Okay? And if it's in tension, it's going to get narrower. All right, any other? So those are the insights. Great, those are insights. Now, I don't know. Let's do a little bit of vocab, all right? So we see that it's wider here, and we see it's less wide here. There is a surface, okay, and it's not my Microsoft Surface. It's a surface that is called the neutral surface that actually does not deform. Can you imagine that? What do we say? What are we talking about, right? We see that, look, this top is in compression and this bottom is in tension. And it's probably, and you can even see, right, this business of the sides, right, it goes wider at the top and skinnier at the bottom. So there is a region, all right, a surface where it does not experience any strain. Okay? This is key. If you are a designer and you have something precious that you don't want to experience deformation, a good place to put it is on the neutral surface, okay? Because it's not going to experience any tension or compression there. And so John Rogers and his research group, they have leveraged this idea quite a bit, this very simple principle quite a bit in flexible electronics. Okay? So even when you take your handy-dandy extension cord, right, from the wall, right, you notice that there's insulation wrapped around it, right? If not, well, it wouldn't be very good to handle. Okay, so if you take that cord, right, and you bend it, right, you have an idea that, oh, the insulation is, part of it's undergoing extension and part of it's undergoing compression, and the material in the middle, if it's close to the middle, all right, and of course you have conductors that have some thickness to them, but the thinner, right, that wire is, right, the closer it is to the neutral axis, you can actually bend it quite a bit, right? And that, yes, nothing is ideal, right? So if I bend it back and forth a lot of times, eventually it's going to fail, right? But you're going to see that the insulation, even though it's rubbery, might fail before the wire itself in the middle would fail. And that's because of the physics of this neutral surface. What else do we want to say here? Yeah, so we already said that, right? Some goes into compression, some goes into tension. Now, let's take our beam and let's break it into a few different sections. So this is a beam, and we're going from left to right here. All right, so this is the beam left to right, and now we're just breaking into sections. Okay, and we're going to call these different sections by their names. So we have like an A, B, D, E, or A, B, E, D section. You have a B, C, F, E, or D, E, F, C, whatever. You have these different sections. And we're going to put a bending moment on this beam, and we're going to look at what happens to A, B, the relative distances between A, B, C, and D, E, F. Right? And you already have now, after we did that whole discussion, you already know what's going to happen. You know that if I apply a positive bending moment, all right? What is a positive bending moment? A positive bending moment is when you have our convention in place, right? And whoop, that means smiley face. Okay? So we're applying, right? You see that? These are our conventions. On the left side, it's clockwise. On the right side, it's counterclockwise. We can see that A and B and C, those are going to get closer to each other, while D, E, and F are going to get farther from each other. All right? So we can call, and you remember we kind of did this when we were talking about the pizza and the torsion on a rod, right? You remember we had all these like stacked pizza slices, and I had a little pizza, and then I was like, hey, how does this location move relative to this location when I twist it? We're doing something very similar here. So D1, E1, and F1, all right, those are going to describe the new locations. And what we're going to see here, okay, is that now there is a center, point O, for the radius, or for the circle essentially that, or the semicircle that we are carving out, okay, with this bending. The length, what do you think we're going to call the length? Well, we did it in shafts too. We're going to call that length, or that radius, rho. Okay? So rho is going to be what we use to describe how far we are from the center, right? And we discussed that C was, okay, and that's not, don't worry, we're not there. But this is focus on rho. But remember, C was the actual radius of the rod or the shaft, right? And then rho was the distance, from the center line to some location. So rho, once again, is going to be what we used to define a radial distance. And then we can see that even though, right, you see A1 and B1, they're closer to each other. D1 and E1, they're farther apart. Well, maybe it's not very clear from my drawing that A1 and B1 are close to each other. But you see this, that we are carving out some angles here, okay? That if I can look at the angle between, A1, O, and B1, right? Or I can look at it from D1 to O to E1, right? And I guess I could have been a little bit more careful and said, hey, this length here between A and B is going to be the same as this length here between B and C, as is like the initial lengths, between D and E and F. Okay, so some other vocab. All right. We just talked about this neutral surface. Okay, and that neutral surface is something that you might find in various texts. And if you open up Hibbler's book, they'll call this the longitudinal axis. All right, this dotted one that goes along that neutral surface that's not experiencing any deformation, at least not experiencing any longitudinal deformation. So they call that Hibbler calls it the longitudinal axis. If you look at Crandall, Dahl, and Lardner's, when I was taking the class, that was called the neutral axis. So once again, I'm like, what's this longitudinal axis? I'm like, that's the neutral axis. So you'll hear me say things like, that's just the neutral axis. Okay? Or you can be Hibbler-like and say, okay, that's the longitudinal axis. Right? But we know typically you're not that confused about what we're talking about. That's the line or the plane, whatever you want to look at the beam, that's experiencing very small angles of rotation. Right? This is super exaggerated, but for our intents and purposes in this class, right, we're dealing in tens, hundreds of microstrain maybe, and the rotations that you're going to get in these situations are going to be small. Yes.
Okay, so just to confirm that I know what we're doing here, if you apply a moment, then the internal bending moment over the entire beam is the same. But
Yes.
if we do the force coming up from the bottom, it does the same effect, but it's not equal over the whole.
Yeah, right. I mean, remember we did that example, right? I said, here's the cantilever beam, and we had a force P on the end, right? And you saw, whoop, there's a slope for the bending moment.
So there's not. Okay.
Right, this is just, so I'm applying an idealistic bending moment on either end, okay?
Then it's equal.
Then it's going to be the same across. Okay, and you're going to get a nice radius of curvature. Okay, so let's take a little bit deeper look at a slice of the beam. Okay, so now same thing, all right, and this is the undeformed states or undeformed elements, okay, in the beam, and we're going to go ahead and take a look at. It could be, this could be A, B, D, E, but really small, whatever it is, right? There's going to be now, but we're now talking really small. And this is going to be having some width of delta x. And the longitudinal axis, or the neutral axis, is going to go through it, right? You see this? We're doing another derivation. All right, and what does it involve? It involves taking a slice. Now, we're going to define a distance. So you saw we had this rho. That was a radial distance from the center line to some location in the beam. Okay? But there's also something that we call y. And this is the distance from the longitudinal axis, or the distance from the neutral axis. Initially, you see that delta S is going to be equal to delta X. Right? Delta S is going to be what is the length between this side and that side. And you can kind of foreshadowing, right? Delta S, as we bend this element, what's going to happen? Delta S is going to change as a function of y. Okay, because, right, remember, if I'm bending with a positive bending moment, then this bottom portion gets wider than this top portion, right? So now we've got this parameter delta S that we could say, oh, that, for very small widths, a line is very much like a curve, right? But let's just say that this is the arc length, if you will, okay? Or the length, either way. So in the undeformed state, delta S is equal to delta X. In the deformed state, which is what we had in the previous slide, okay, what's going to happen? We're going to have this delta S now varying, okay, as a function of y, okay? But first, let's set things up, right? This is the delta theta, right? This is going between, let's say, A1, B1, E1, D1. And we had this thing that we called rho, and that's just describing some distance to wherever we are, okay? And let's say that distance is, going to the neutral axis now, and we can say that this delta X is going to be unchanged along this longitudinal axis. So the delta X, all right, here is the same as this delta X here. And what do we do next? Well, we can define the new delta S, okay, as a function of y, as what we'll call delta S prime. And how do you relate strain to changes in length? What's the definition of a normal strain? Yeah, it's the delta in the length, right, divided by the original length. Okay, so what do we have here, right? We have a change in length, right? Like a delta S minus a delta S prime, right? And what's the original length? Delta S or delta X, right? So now we have a way to figure out what the normal strain is as a function of, well, a few different things, but y in particular, okay? And rho. So now we have this is just copied and pasted, all right? We have the same diagram, and we're gonna say at some location, okay, so specified by distance y, right, we can have, from the longitudinal axis, all right, we can have some delta S prime, right? We already said that. And if we do a calculation of the normal strain, right, what we can say is this epsilon at some distance y is going to be the delta S prime minus delta S over delta S, right? We just verbally said that. I didn't say the limit of that, right? And if we look at things, we can say that, okay, the original delta S was equal to delta X. And here's a new thing. If we say rho is the distance to the neutral axis, that rho delta theta is also equal to delta S and delta X. Okay, that's the arc length. Okay, and so now, okay, what is this what is this essentially this delta S prime? Right, this delta S prime, look at it. Rho minus y, right, is going to be a new radius to here. Okay, you see that from the O to here, that will be the new radius, and if I multiply by delta theta, that gives us the delta S prime. So this is delta S prime is equal to rho, quantity rho minus y delta theta. And we do a little bit of algebra. Okay, so what do? We said, oh yeah, this delta S prime is this, boom. This delta S is this, rho delta theta, boom. That's right there. Rho delta theta is the denominator, boom. And then we write out that we can divide everything by, or we got the delta thetas all over the place, right? And then we have rho minus y minus rho. Okay, well, rho and rho are going to knock each other out, and we get that the strain is equal to minus y over rho. This equation is not something that you're going to write home to your parents about. Okay, maybe the next equation we talk about on Flexure Formula would be something to write home about your parents. I don't know. My parents probably wouldn't care, but maybe some of your parents would care. It's like, hey, I learned the Flexure Formula. It's like, yeah, all right, that's great. Welcome to the club. Okay, but this is not that yet. But we're going to use this equation, all right, as we go further with our derivations. Epsilon is equal to minus y over rho. And you should, of course, write this equation on your notes for the next exam. Okay, so here's some assumptions. The longitudinal axis on the neutral surface does not experience any change in length. It curves. True. Okay, so we already kind of said that. All right, that this is where you don't have any change in the length. All cross-section planes remain perpendicular to the longitudinal axis. So this is just kind of saying, if I am interested in my bending moment and my shear force at a particular location, I take a slice, all right, and it's going to be perpendicular. It's not very clear here, but it's perpendicular to the longitudinal axis. Okay, that's nice. We're going to ignore any deformation of the cross section within its own plane. All right, so yeah, we're just not we're not going to care too much about what's happening in the plane that we're slicing. And the normal strain is going to vary linearly with the distance from the longitudinal axis. That we've already said, and that is true. So what does this look like? Okay, this looks like the following. Here is just a like A, B, E, D element. All right. Here is the delta x for that. All right. There is no change in length of this dashed horizontal-ish, like curved line. Okay. There is a opportunity, okay, to go ahead and write out, okay, that the strain is going to vary as a function of y. And do you see that just using, this is using that formula that we just described, right? Except now we're saying that we have, before it was minus y over rho. When you get to the outer surfaces, that strain is going to be the most positive or the most negative. Okay? And so sometimes what you'll see, this is often more used to describe the stress along a beam at a given location, but here we're using to describe the strain. What do I mean? I mean you have a line that has a slope that goes through 0 when it's at the longitudinal axis or at the neutral axis, and it increases or becomes less negative, or becomes more negative, or becomes more positive as you move away from that longitudinal axis. Okay, everyone see that? And it maxes out at what, and here is the C. This is a different, it's not the same C as in the radius of a shaft, okay? C is now going to become the thickness, all right, or half the thickness, okay, of a beam. Okay? So here what you see is that there's some slope here, and we can say that there's some maximum strain here. And if I go hey, what's the distance between the longitudinal axis and the surface, and I call that c, I can write out this expression. Okay, any questions on that expression? We don't know what epsilon max is right now. Okay, we're just saying that it's a max at the surface. And we, so it's a max at the surface, but we haven't related that directly to, say, a bending moment. What we've described so far is a strain. Right? A strain is equal to, right? We go back here. That's what we know at this point. We know that we have a strain is equal to minus y over rho, but we don't really have a way of saying, hey, that rho is this for a given amount of bending moment, because it's dependent on a few different things. Okay? All right. So for a positive internal bending moment, the region above the longitudinal axis is in compression. And again, we've said that already. And the corollary is going to be that the region below the neutral axis is going to be in tension. Okay. So now, here's the cantilever beam with applied moment. And when we have a thickness of 2c. Okay, that might not be clear. That's 2 times c, that's the thickness. Where is the maximum bending strength? It's not a trick question. Yes? Yeah, exactly, right? It's going to be at a distance c, okay? And so, if we draw this thing out like this, right, it's going to be where we have c, okay. And this is equation, gives strain at an arbitrary distance, and the maximum bending strain is going to be where we have y equal to plus or minus c. Okay. So it's very important to remember that the maximum bending strain will be along the top or the bottom of the beam. Okay. If the strain is a maximum at a given location, what does that mean about the stress? Assuming that we have a linearly elastic, isotropic material. It means that the stress is also going to be maximum there, right? Hooke's law, in whatever form we take it, right? Sigma equals E epsilon, or, the strain is equal to 1 over E times quantity sigma x minus nu times, quantity sigma y plus sigma z, whatever we have, right? So that's where we're going to start seeing the maximum bending stresses as well. So have you ever thought about that? There are a couple maybe I'm getting ahead of myself, but there are a couple interesting things that this means. It means that your beams are experiencing maximum bending stresses at the out the outer surfaces. It also means that if you can strengthen the outer surfaces of these beams, that will prevent failure, right? Because there's no strain on the longitudinal axis. We just talked about that, right? So if you're worried about trying to make something that's going to be under bending stronger, what you want to do is you want to make the outer surfaces stronger. Yes?
Is the top always going to be like a circle?
Well, if you have a nice, pure bending moment applied, yes. But will I give you that on an exam? No. Okay, unless maybe it's a thought question, right? But we're going to have transverse loading like a P, a couple force. A couple moment, applied force, right? External force. It's going to be more complicated. Distributed force, right? Yes.
So just to clarify, the rho is always measured from the center of the radius of curvature, whereas the c is always measured from the neutral axis.
Okay, so what I tell my kids about superlatives is try not to use them. You know, maybe I'm creating politicians, I don't know. So always is a strong word, all right? But yes, the rho is going to be what we usually use to define the angle of rotation, okay, between some center, right? This center can be moving, all right? There could be multiple centers, right? If it's not a perfect circle, you know, you could say, oh, well, this is what, you know, at this location, since I know this is the strain and this is the y, that's the rho, okay? And yes, the y is the distance from the longitudinal axis, and then c would be the distance between the longitudinal axis and either the top or the bottom, okay? And there are ways, and that's, you know, the neutral axis doesn't always have to be smack dab in the middle. Okay, it's at the centroid. Okay. All right. Now, the Poisson ratios effect. All right. The portion and compression can have a larger cross-sectional area with deformation. The portion and tension can have a smaller cross-sectional area with deformation. Yes, we believe this. All right, and we need to keep going here. But epsilon y is equal to nu minus nu times epsilon x. Okay, this is a true statement. And epsilon x in our case is along the longitudinal axis. Okay, and the same thing for epsilon z. All right, so let's keep going. There's a question. Yeah, you have a question on this. This one's pretty straightforward, and it's pretty much just using the relationships that we said here. Okay. Now, bending stresses. We've already defined the normal longitudinal strain. Okay. And if we look at this from the side view, right, you have this relationship that epsilon is equal to this quantity minus y over c times epsilon max. Okay. Now, Hooke's law tells us that for a uniaxial case, sigma is equal to E epsilon. A bending stress is going to be what is the stress due to this strain. Okay, so you see what we've done here? We've said, oh, there's a minus y over c. Okay, keep that. There's an epsilon max. That's fine. I'll call it sigma max, and I'll divide by e. That gives me epsilon max. All right, and epsilon is just equal to sigma over e, so I put that on the left side. Okay, right? So this is why that relationship was so important. The epsilon equals minus y over rho, okay, is now going to give us a pathway towards calculating out what the stress is. And yes, we do care about deformations, but it doesn't really matter in a design, from a design perspective, if you have the ability to calculate deformation, but your stresses are through the roof and the thing is breaking, okay, or yielding. And this is something you should keep in mind when you do finite element. Finite element, at least with kind of linear elastic materials and not complex models, it's just no matter what going to give you a bunch of stresses and it's going to give you a bunch of deformations, right? But if you don't compare those stresses and deformations to, well, the material limits, it's kind of garbage, right? So anyway, that was another kind of digression. But what we see here is that we have now the ability to say that there's going to be some bending stress, sigma, which is going to be equal to minus y over c times sigma max. Again, that is not super simple, or not super useful, I guess, because now I don't even know what sigma max is. Okay, so what do we do? All right, what do we do? Well, we're going to take a look at how we can visualize the stresses that are on a sliced surface. Okay, so you see this? Here is, right, you got this idea, right? We said if I have a bending moment, a positive bending moment, the bottom region is under tension, the top region is under compression, and it's varying linearly, right? We've established this now algebraically as well. And if I think about all these stresses, and I take some dAs, right, some small areas, I can think about, oh, this is like a little bit of force. This is a little bitty force, a sigma dA. Okay? And force offset from a distance is a moment and a torque. And we have moment. Okay, so you see where this is going to go? Now, there's going to be something that we have to introduce called the first moment of area. We'll get to that in a second, but here we have sigma equals minus y over c times sigma max. We can say that the summation of the forces has got to be equal to 0. And now we're saying that a force can be the integral of sigma dA. So if I take, the sigma dA over this entire cross-sectional area and I sum them all up, that has to be equal to 0, right? Because that's what the second law tells us with statics. When the acceleration is the surface is not accelerating, right? So now we plug in this equation here, and we get this idea of an integral of y dA is going to be equal to this minus sigma max over c. This integral y dA is something that people call the first moment of area. Okay, and this is useful for a variety of things, but in particular, it's also helpful for figuring out where the centroid is and where the longitudinal axis is. So this would tell you the height of the longitudinal axis in the vertical direction. And we won't cover that right now. We'll cover that a little bit later. But that was our discussion of equilibrium for the forces. Okay, this is an equilibrium for the forces. What's our next type of equilibrium? Equilibrium for the moments. Okay? So when we have this cross-section, now we'll say, hey, the moments, all right, the summation of the moments that's got to be equal to some moment m, all right, because we see that here. And we can say that m is equal to this integral y sigma dA. Remember, we're saying y is the distance away from the neutral axis. Sigma dA is the force at a particular small area. Okay? And these dAs could be slices across the entire beam now, right? Because we have a y and we have this sigma dA. That dA could be across the entire cross-section. Okay. And then we have this integral, right? So we have y sigma dA. Sigma can go in here. This is that big mess. We had y here already, and we had another y, so that becomes y squared. And now we have that the moment is equal to minus sigma max over c, and this integral of y squared dA. This is a geometric. Both the first moment of area and the second moment of area, those are things that are dictated completely by geometry. You see that? There's nothing inside of this that says force, moment, stress. This is completely based on the geometry of the cross-section. And then we define this second moment area as integral of y squared dA, right? Okay, that's I. Sorry, we define it as y, sorry. And the moment then can be written as minus sigma max over c times I, and the sigma max is equal to minus m over c over I, minus mc over I, or we can say that the Flexure formula tells us that sigma is equal to minus my over I. You see that? Because this is the maximum, right? But if y is equal to 0, then it's 0 at that location, right? Because there's no strain there. There's no strain there. There's no stress there. So and we said it varies. That strain is going to vary linearly from the y equals 0 to the y equals c, the outer location. So now we can just plop in y instead of c, and that gives us the bending stress. This is a historic equation. This is one that you want to have in this class, in DMC, and many of your other classes. Okay? Ask your upper class peoples. All right? What equations do you use after mechanics and materials? They'll say, well, we use, sigma equals E epsilon, yeah. But then say, hey, do you remember the Flexure formula? And if they say no, then you say, you better go talk to, Aaron about that, because he wants to meet with you. No, don't say that. But this is one of the key formulas that we all want to remember. Okay? So question 2, which I guess I will take some time to do with you all in a video afterwards, we'll refer to this equation. And if this is the simple beam, not with a constant bending moment across it, right? It's with a varying, it goes from minus PL to 0. And the maximum, right, is going to be dependent on some other things. All right, so let's talk about second moment of area briefly. Okay, and actually, I think I might have to put this in a video as well because we're running out of time. Briefly, though, the second moment of area is this integral of y squared dA, and there are going to be relationships that you learn, okay, that will also stick with you forever. Okay? That's one of them. So for this given cross section, okay, you're going to have this thickness having a very large effect on the second moment of area. The second moment of area, right? So we talked about minus my over I. In a lot of respects, right? If I is really big, that means the stress is going to be small for a given amount of m, right? Sigma equals negative my over I. So a lot of times you want to make it large, but not too large, because otherwise you got to use a lot of material, right? And it's going to be heavy. So you're thinking about how do I make a big I so I have a low stress from bending, right? That's a design thing. So if I look at a cross section, and this is kind of classic, right? If I take a piece of paper, I don't know, this is someone else's piece of paper, right? Is the thickness large? No, flipsy flopsy, right? If I turn it sideways, is the thickness large? Yeah, very, very rigid. Now there's some buckling going on here, okay, so yes. All right, but you see, just by taking your structure and flipping it to have a large cross section in the direction or corresponding to the thickness relative to the bending moment you applied, you make a big difference. So if you're building a bridge, maybe you want a lot of vertical type of thickness, right? And how do you do that? Well, I-beam, right? That's how you can get that high I with using a very little amount of material. And so that's a structural effect, right? A structural effect of, okay, I want to have a high I so I can handle large stresses, but I want to keep weight down. Okay. So I'll go through some of these questions. Of course, you can answer the questions without going through my extra videos, but the extra videos should help you be able to answer the 3 questions that we have. Any questions? I got 3 minutes, so you're okay, everybody, but let's go ahead and we'll do the attendance. I appreciate everybody's cooperation, but any questions while we're getting to this? Okay. All right. I'm a little nervous. What is going on? I don't know. Well, we'll try one more time, but if that doesn't work, okay, there. I don't know why it didn't work. All right. Go ahead, take your attendance. And we'll see you on Friday. Thank you very much.